Okay, everyone, we ready? 2 classes left. All right, so I've decided on the mini exams, since most of you are going to be doing your review anyway and trying to work out the problems. If you turn that in, attempted, meaning you did your best on it, and turn that in, I'll send a Dropbox link for that. Then I'll count that as mini exam 7, and then I'm thinking for mini exam 8. I might have you watch a lecture video on the last section of the book, which I don't think I'll get to, and then ask you to do a few problems regarding that section. So we'll see how things go. Mini exam 7 for sure. Just turn in your completed the review. Mini exam 8 is a question mark. Our finals next Wednesday. All right, let's get down to business because we have lots of business to do here. Last class, we had started talking about surface integrals. We had spent time figuring out how to come up with surfaces, right, using parametric equations, R of UV. We spent a lot of time doing that. And then towards the end of class, I showed you how we can use that to actually find the equation of a plane that's tangent to some surface. When we did this problem, we actually had to do a calculation here. When we were doing that, what we had to do was look at the vector equation, or the vector equation of the surface. We had to take the partials, the two partials of that vector equation. Here were the two partials, and then we did the cross product of those, and that gave us the normal vector for the plane. The reason I'm bringing this up is because the next thing we're going to do, I'm going to need this information. So I just want you to be able to refer back to your notes from the last class. This draws the unit sphere. Here are the partials, and here's the cross of the partials. Okay, so picking up from where we left off, we get to now what are called, what is a way that we can find the surface area of one of these surfaces that we now know how to draw. And so there's a geometric explanation. If you're trying, let's say we take the unit sphere again. We know the vector equation of the sphere, right? That's right there in our notes. It's this right here. This draws it. Now, if we know how to draw this and we want to know the surface area, then what we'd like to do is take like a little small patch of that surface. And, here's our two, these are our two partial derivatives. There's two vectors that give us, these two are the partials with respect to u and v. And so that's how we created that tangent plane. But if we're trying to do surface area, what we need to do is imagine taking that and looking at a small little infinitesimal little patch down here. Now, we'll just use the red patch as an example. Zoom in on that. So you can see that those vectors create a little plane that's really close to that red patch. And the smaller we go with those vectors, the closer, like in the infinitesimal, we should be able to approximate the red patch with something that has to do with that tangent plane. So if you recall back from our notes way back in the beginning of class, if you're given two vectors and you want to know the area of the parallelogram formed by those two vectors, u and v, then the area is just the magnitude of the cross product of those two vectors. That's all it is. And we use this to actually find the area of a triangle, but this was the formula. Now, with that in mind, what we want to do is imagine taking that little infinitesimal patch, right? Finding the area of that little thing. And then we have to scale it because those vectors, the partials, let me make this a little bigger. Remember, the partials are vectors, right? So if we do the magnitude of the cross product, that's right here in the formula, see that? If we just do the magnitude of the cross product of those two, then that's going to give us this big area. We need to scale it down Okay, and that's what the dA is. dA is this infinitesimal patch, just like the dx was in our normal Cal2 integral. The dx is our infinitesimal little change in x. So that's it. I mean, this is the formula. It's a very straightforward formula. If you are given a surface, you have its representation using a vector equation. You have restrictions on the u and v, so the u and v are in some domain. Then all you're going to do is the double integral over that domain of the magnitude of the cross product of the partials. So let's take a look at the surface area of the unit sphere, right? If we have the unit sphere, we can find its surface area using that formula. So let's do that. Okay, so here we go. So the first thing we need is we need to know what the surface, how we draw the surface. So we knew from last class, that's how you draw the surface, right? And we're going to be trying to do the double integral over d of the magnitude of the cross product of the two partials dA. Now, again, last class we did the cross product. Here it is. Let me grab this. See if I can grab this. That may have grabbed too much. Let's see. So there's our cross product. And if we take the magnitude of this, so the magnitude of that cross product, well, that's just the square root of the sum of the squares of each component. So I'm just going to square each of these. This becomes sine to the fourth u cosine squared v plus sine to the fourth u sine squared v plus, now all of this simplified to be this, so it's just going to be cosine squared u sine squared u. All right, that's the magnitude of the magnitude of the cross product of the partials. And then I notice on my first two terms, they both have sine to the fourth u. So if I factor that out of just these two, I'm left with cosine squared v plus sine squared v, right? Which would be a 1. Go with me? So that leaves me with just the sine to the fourth u. That's what all of that becomes. And then I have over here still plus cosine squared u sine squared u. And on those, I can factor out a sine squared u. I'll go ahead and show this one. And when I do that, I'm left with sine squared u plus cosine squared u, which again turns into 1. So we get the square root of sine squared u, which is technically, and I had a conversation with one of your classmates about this. This is technically the absolute value of u, or sine of u. Anytime you take the square root of x squared, most of the time it's x, but technically it's the absolute value of x. It's only x if you can promise me that x is greater than 0. If you can't promise me x is greater than 0, then the answer is the absolute value. So this technically should be the absolute value of sine of u. However, if you go back and look at u is restricted between 0 and pi, and the sine function on 0 and pi, here's sine. So this is, the period is 2 pi. So if you're only looking from 0 to pi, sine is always above the x-axis, so it's always positive. So that means we can just say sine u. But it's only because of that restriction that we can do that. Okay, that's good, right? That all turned out to be something pretty nice. So back up to this. This becomes the double integral over d of sine of u dA. And now we just need to put our restrictions on u and v. So I'll go from 0 to pi, 0 to 2 pi. We're integrating sine of u. Let's see, my u's on the outside, so dv du. Any questions? Move this down here. Any questions? It doesn't matter what order I put these in, just as long as I get the limits of integration correct. Now it's time to integrate. So the antiderivative of sine of u is negative cosine of u. Sorry, I'm integrating with respect to v first. Sorry, it's just v sine u, 0 to 2 pi, and then we'll do du. I apologize. This becomes integral 0 to pi. Okay, antiderivative, I'm sorry, we already did the antiderivative. Plug in, for v, we're plugging in 0 and 2 pi. So you should just get 2 pi sine of u du. You with me? Okay, the antiderivative now with respect to u should just be negative 2 pi cosine u, evaluated 0 pi. We good? Okay, be careful on this. Equals. All right, let's do two things here. All right. So when we plug in pi, we get negative 2. Cosine of pi is negative 1. Now let's plug in 0. So when we plug in 0, we get negative 2 pi, and cosine of 0 is 1. So times 1. And I'm out of room. So this is going to turn into, let's see, the first part's 2 pi, right? And then minus minus, so it's plus 2 pi. So your answer is 4 pi. So the area of a sphere of radius 1 is 4 pi. With me? Okay, here's something cool. What if the radius of the sphere was, let's say, r? Right? What if it was r? How would things change? This might be hard to show, but I'm going to try it. So let's say our radius was r. Then when we draw this, r would be like the row. Okay, so it would be an r here, r here, r here. Okay, how would that have changed our partials? Well, r would have been a constant, so r, and then we would have had an r right there. And then this partial would have an r in it also, and this would have an r in it, and this one would be 0 still. When we did our cross product, right, when we cover this up and do our cross here, this would give us an r squared there. On this one here, we would get another r squared there. And on this last one, we would also get an r squared. So that means when we did this part, when we did this, we had our r squared here, r squared here, r squared here. We would have had r squareds, we would have had r to the fourths on these because we would have squared those when we found the magnitude, r to the fourth here, r to the fourth. When we got to this point, we could have pulled r to the fourth out of everything and then pulled it out of the whole thing as an r squared. So we would have had sine u r squared. Do y'all see where this is headed? We just would have had r squareds and then, crap, where'd it go? Okay. And so when we went to go integrate, the only thing that we would have here is we'd be able to pull an r squared out of this and just carry it the whole way through. And so at the very end, our answer would have been 4 pi r squared. And that is the surface area formula for a sphere that you could look up on a formula sheet, right? But this shows you where it actually comes from. Pretty cool. Okay. All right, moving on. All right, now, there are some special cases, and today is going to be a lot about special cases, but if we're trying to find the surface area of the graph of an equation, when you think back to a sphere, right, to draw a sphere, that is not a traditional surface where you can look at it as like a function of two variables because it wraps around itself. So we use spherical coordinates for it. But if you do have a surface, like when we first started talking about surfaces, that's floating up above and you have some domain on the ground. In other words, if your z is some function of x and y, right? You have this special surface, then something very nice happens when you try and do all these partials and crossing. Okay, when you do that, you get a very, very nice result at the end. So I'm gonna try to briefly take you through, what's happening here. So let's say that what you have is z is some function of x and y. Okay, then what we've been dealing with is we've been saying, hey, let's try and draw a surface with this vector function r of uv like this, right? And we've been coming up with these things, and that's what we spent last class on. Say, look, okay, instead of that, let's do this. Let's call it r of, instead of u and v, let's just use x and y. And since z is a function of x and y, that means that x is just x, the y is just y, and this last part is the actual function of x and y. So that's our vector function. This is it right here. And now when we do the partials, you know how originally we do partial of r with respect to u, and then we try and cross it with partial of r with respect to v, and then we would take the magnitude like that to get the surface area. Now what we do is we do the partial with respect to x. Okay, let's see, what would the partial of this with respect to x be? Well, 1, 0, and then whatever the derivative of this is with respect to x. So see how I wrote that f subscript x? Then the partial of this with respect to y would be, well, if this is x, that would be 0, and then that would give you a 1, and then this would be partial of f with respect to y. And now when you cross them, this is the nice part. When you cross these two, this is where things are nice. So if you cover up these and do your little cross product here, or your little determinant, I'm sorry, you should get for your first part negative partial of f with respect to x. Then when you do the middle one, you get this times this minus this times this, but then you change the sign. So you should get negative partial f with respect to y. And then when you cover up the j component and do your little determinant here, you just get 1. And then when you take that magnitude, you get square root of, well, when you square these, the negatives go away. So you get 1 plus, I'm changing the order, partial of f with respect to x squared, partial of f with respect to y squared, and that's it. That's what that note was saying. Now, I used a slightly different notation here, but it's saying, look, if at the end of the day, you're looking at a traditional surface where it's a function of x and y floating above the xy plane, then instead of doing all this crazy stuff, just do this, double integral over d. This is already the cross product stuff done. You don't have to go do it. It's already made for us, okay? You're just going to take the square root of 1 plus the partial of f with respect to x squared plus partial of f with respect to y squared dA, and then you'll have to work out the domain. You'll have to figure out how x and y fit into things here. Okay, so this is a nice shortcut way of getting surface areas, so long as the surface looks a certain way, like in this example. Find the surface area of the part of the paraboloid z equals x squared, y squared minus x squared, which lies between these cylinders. Okay, so let's see if we can figure out what the hell's going on here. All right, so we kind of have to know what a paraboloid looks like, right? This right here, we kind of have to know what that looks like. You go back to the section we did on quadratic surfaces. This looks like in one direction it looks like a parabola that goes up, but then another direction looks like a parabola that goes down, right? It's like the z is either going to be like a parabola going up, or negative x squared is like a parabola going down. So it kind of looks like a saddle. It's really hard to draw that type of paraboloid, okay? What we need to understand, though, the most important thing is that this z is some function of x and y, right? It's some surface. Now I know this isn't what it looks like, okay? But that's it right there. It's a traditional like blanket floating in the wind. And if we're trying to find the surface area, then we know that we can use this double integral over d of the square root of 1 plus the partial of f with respect to x squared plus the partial of f with respect to y squared dA. Okay, we know we can do that. The thing that we have to figure out is what does the domain on the ground here look like? But it says here that we're supposed to be looking at the surface area of the part of the paraboloid that is between these cylinders. So those two cylinders I expect you could draw. You have a cylinder here, radius 1, that goes up, right? Punches through your surface. And then you have a larger cylinder like this, comes up and punches through your surface somehow like that. And you're trying to find the area on that surface between those cylinders. Do you understand geometrically kind of what's going on here? My computer can do a much better job. There it is right there. Okay. There's your paraboloid, and you have an inner cylinder that's cut out. See, the cylinders have cut out pieces, and you're looking at the region between them. So that's where you get this from. Okay. So this part I think should be easy. The function of x and y, I should have put it up here, is y squared minus x squared, right? That's our function of x and y. No problem. I can find partials of that. That's easy. Partial with respect to x is just negative 2x. Partial with respect to y, that's just 2y. I'm in business here. Double integral over d, square root of 1 plus, okay, if I take the partial of this squared, I get 4x squared. Partial here squared, 4y squared, dA. Now what I need to do is figure out what this d is. And the d is the shadow of this thing down onto the ground. And this is where it's just important that you understand that the shadow on the ground is this little washer on the ground. And if that's your region on the ground, if that's what d is, should we stick to Cartesian or should we go to polar?
Go to polar.
Let's go to polar. I mean, that's a perfect polar region. So d, the way I can express it is I can go ahead and make a substitution to polar. X is going to be r theta, r cosine theta, y is going to be r sine theta. And now let's discuss the restrictions on theta and r. So we want to go all the way around, right? So 0 to 2 pi. And our radius, this one's a little tricky. What's the radius here? The inner one has a radius of 1. The outer one is radius of 3. So I should stick between 1 and 3 on this, shouldn't I? So we're going to go to polar now. Double integral, I can go, let's go 0 to 2 pi on the outer one. 1 to 3 here. Square root of, okay, now this looks like a mess in here, but y'all see if you pull a 4 out of there, you get 1 plus 4 times x squared plus y squared, but what's x squared plus y squared in polar?
R squared.
R squared, right? R squared. And then what's the dA part become?
dr d theta.
Dr d theta. I left a space. Why did I leave a space?
The Jacobian, so R.
That's right. We went to polar, right? We went to polar. Don't forget the R. You had to put the R in there because we went to polar. And that's it. That integral is actually very easy to do because if you let u be this, the derivative of it's over here, we're off by a constant, but this is a very basic substitution problem from Cal 2. Now, there's a lot of problems that we're going to try and do today. And so I already had the computer. Whoa. Hold on a second. I lost everybody. Okay. I already had the computer do this for us just to save us some time. because I would expect that you could do that by hand. So that integral, the integral from 0 to pi, 0 to 2 pi, 1 to 3 of the square root of 1 plus 4r squared r dr d theta is equal to this. Now, when I did it, I got same answer, just looks a little different, but so I'm going to stop there. Okay, I'm going to stop there. If we wanted to do it as a like a decimal, it's about 111.988, whatever, square feet or square meters, square inches, whatever unit we're measuring it. I don't know. I mean, it's pretty badass if you ask me. Like, that seems like a pretty hard question to answer walking in today, right? Like, hey, you know, find the surface area of that, which lies in, like, if I showed you that and I just said, hey, find that surface area, I mean, that probably seems like that would be a pretty tough thing to do. But as long as we can kind of keep our heads wrapped around what's going on, it's not that hard. Okay. That's it. That's it for this section. All right. We need to move on. All right, 13.7, this section is a monster. So I sent everyone a file today in Canvas called 13.7 recap. And then I realized later that I wanted to do one more thing and just update something on it. So I sent it again. And what it looks like is this. It's a bunch of stuff. It's a bunch of formulas. And I know it looks crazy right now, but you know, it's all going to be crystal clear by the end of today. I'm kidding. All I did in the second version, all I did was next to each one of these formulas, I put an A, B, C, D. That way, as I'm going through class, I can actually say, hey, look at D or look at E, or in that way, it's easier to reference, okay? Okay, 13.7, here we go. Surface integrals. So this is a definition to start. Given a scalar function, f on a surface S with vector equation of the surface given by some parametric equation, then the double integral over S of the scalar function with respect to S is this. Okay, so what is this? What is this? You know how what we just did, let me bring that back up. Okay, so what we just did was we took a surface like this and we found the surface area. But what if instead we were looking at this object as being like a lamina? Remember when we were talking about laminas, like a sheet of paper? We had a way of finding the mass of a piece of paper if it had a non-uniform density. Think of this the same way. Imagine this is some like weird lamina shape, and we somehow know its density at every point. So we have some function that tells us go to any point on this surface you want, go to any point, and I can tell you the density there. Then if we have that, then there is a way that we could find the total mass of this object. And it would be by adding up all of the infinitesimal masses at each point. And so it's different than the surface area. We need the area of the surface, but it's almost like we need to multiply each little infinitesimal patch of area by the density to get a mass. And so that's basically one way you can look at this. It's everything we did before, right? This is what we did before, but what we're now adding to it is some scalar function that's going to tell us at each point, like something like the density. And so when we multiply these together, we get something like a mass. Another way you can look at that function, maybe that function gives you the temperature at each point, or the electric charge density. And so this integral would represent the total charge on the entire sheet. So do you see that it's just an extension of surface area in the sense that you're adding this new component to it, this new piece that at each point, you're not just looking at area, you're looking at area times something. That kind of makes sense? Mm-hmm. All right, so the formula is nothing crazy. It's stuff we've been doing already. I mean, like we already know how to do that, okay? So it's just this new piece right here. So let's do this example. What I'm gonna do is I'm gonna take this. Oh, you know what? This, I believe, hold on. I believe this is formula A. Double check on your formulas.
Can I ask a question?
No.
Okay.
No, of course you can, Daniel. What's up?
If our scalar function f is dependent on x, y, z, then how are we plugging in a vector function of two components? Oh, never mind. Never mind. That could return R3. I'm forgetting that.
No. Good question. This right here is a notation that's weird, right? We're taking a scalar function and we're plugging in a vector. But that vector is a three-dimensional vector, so it has an x, y, and z, and that will replace the x, y, and z in the function. Good question. Good question. Think you were thinking two-dimensional. This needs something three-dimensional, right? That's what you're thinking?
Yeah, I was thinking
But,
two-dimensional in, two-dimensional out for.
Yeah, exactly. Okay. All right, so let's do this problem right here. Find the surface integral over the surface S of, okay, here's our scalar function, x, y, z ds, where S is the part of the unit sphere above the cone, z equals the square root of x squared plus y squared. So for those of you who did this one in the mini exam, you might be familiar with this. This is this top part of this cone. So we're not looking for the surface area of this. We're looking for the surface integral over that surface. Here's the scalar function we're evaluating. So again, if for some reason this gave us like the density at each point, then what we'd be finding here is like the total mass of this thing. Okay, the mass of this little surface top. All right, let me copy this. Now, debating. Shit, what am I doing, Norman? Yeah, this is the way I'll do it. Okay, so if I were to do this right now, here's what I would have to do. I would first realize, just for the sake of being clear, the scalar function we're dealing with here is the function x, y, z. Okay, that's our scalar function. Now, the surface that we're interested in, that top part of that, I'm just going to put it like that. It's the top part of the unit sphere. That surface S we have to be able to draw it, okay? We have to be able to draw that surface. Now, can we draw that surface? Do we have some vector function R of UV that will draw us just that top piece? Well, we should, right? Let's see here. We know how to draw the sphere. And then cosine, you know. Okay, so this should draw us the unit sphere, but it draws the whole thing. If I let u go between 0 and pi and v go between 0 and 2 pi, it draws us the whole thing. We don't want the whole thing, right? We just want this. So how do we figure out, if this is straight up, how do we figure out what this angle here is this is U. It's like the phi was. How do we figure out how far we come down? How can you determine that from what you're given here? Is there any easy way to do it?
I mean, with this one, I look at the side of it from the like YZ plane. And
Yeah, okay, so we
it comes out to be 45 degrees.
yeah, we have a sphere, right? And then we have the cone, which is right like that. And then we have this little top piece here. That's the part we're talking about right here, right? So the question is, you know, that angle there, we can look at this like a cross section. We take that unit sphere, take a cross section of it. Let's say that this is the XZ plane. Then the cone would come in here like this. And here's the equation of the cone. I think this is where things get easy. So do y'all see what I've done is I've cut the sphere in half and I'm looking at a cross section of it. So it's almost like I'm looking from down the y-axis, I guess you could say, looking towards the cut. If I'm looking down from the y-axis, do y'all agree that this cone equation, the y is 0? In this picture, the y is 0. So if y is 0, that equation becomes z equals square root of x squared, which means z is the absolute value of x. That's the picture we're seeing here. But we should all be comfortable with the fact that if this is absolute value of x, then this is 45 degrees, right? And so we wanted to know, you know, what was that angle over here coming down? What was that u? Well, it's 45 degrees or pi over 4. And that's important because we need to restrict our u between 0 and pi over 4. And then our v, that we're going to swing all the way around. That's our v that swings us. So we've got, you know, from straight up, we go 45 down, everywhere in between, and we spin around, right? And the distance we are out is fixed at 1, which is why all of these have 1s in front of them, right? And that should draw that little cap. Okay. So we have our scalar function. We have our curve that we have the function that draws the curve. And what we're doing is and this is formula A on the sheets that I sent out today. It's this one right here. Oh, you know what? Let's do this. I have it right here. Here's formula A. So this one right here. So we're given a scalar function and a surface S, and we have the vector equation of the surface. Then we are going to need to do this right here. So I need to do this. Okay, so I want to do the double integral over D. So I'm doing this. Now, the scalar function, which was this, I'm gonna have to slap it down here. There's our scalar, and then here's our vector function here. Okay, so what I want to do is I want to take the scalar function x, y, z and evaluate it on this curve. So, or on this surface. So that means I'm going to replace x with that, y with that, and z with that. So it's just going to be x times y times z. So it's this times this times this. That sucks. Okay, so let's do it. It's sine u cosine v, sine u sine v, cosine u. Okay, that right there is that, right? Times the magnitude of the cross product of the partials. We did that already, right? That was what, just sine u, wasn't it? Just sine of u. because we're on the unit sphere, right? It's just sine u, and then dA. And that becomes double integral over, let's go ahead and do this. Let's go 0 to 2 pi, 0 to pi over 4.
I've got a quick question about
Yeah.
restriction on u. Isn't it supposed to be from pi over 4 to pi over 2? Or am I seeing it wrong?
Remember, u is like phi in spherical coordinates, and it always starts pointed straight up.
Oh, okay. Okay.
And so it goes from 0 to pi over 4. I think what you're thinking is this is 0, and then this is pi over 4, and that's pi over 2.
Yeah.
Okay, yeah, phi always starts from pointed straight up.
Okay.
So 0, pi over 4. Okay, I can put some of this together. Sine cubed u. I have a cosine u in there. That takes care of that. And then I have a sine v, cosine v. D, let me see. Du first, then dv. That's it. It looks bad, but it's actually not that bad. Could you integrate this with respect to u? These are all constants, right? So antiderivative, that's just a basic u sub, because this is like this, the derivative that's right next to it. So you can just do a basic u sub here. And then when you get to the v's, it's the same thing. Just, you know, here's something, there's its derivative, that's another basic u sub. So you should be able to do that. Now, again, to save us time, I'm just going to have the computer do it. Oh, did I not do this one? I guess I didn't do this one. Let me see, I did it by hand. Oh, no, I didn't do it by hand. Oops. Oh, well, we'll just leave it. You get what you need to do, right? All right, so that's it. Okay, now, some applications. This is what I was talking about a second ago. If your surface S is some sheet, right, with some density function, then if you do the surface integral using that density function, ds, that's going to give you the mass. And you can actually go find the center of mass of it using these formulas. Now, I'm not going to test you on this, but this is just so you know, like this is similar to what we've done in the past, but now we're in a three-dimensional surface instead of a surface on a flat, like on a flat plane. Okay, so do you remember when I was saying that when we're trying to find the surface area? I keep on closing that section, damn it. When we were doing the surface area just a moment ago, I gave you the formula we started class with right here, okay? And we found the surface area of a sphere. But then I said, hey, look, in the special case where our surface is floating up, you know, like this one, then the formula simplifies and it gets a little easier to use. And here it is. Same goes for surface integrals. If you have a special case where z is some function of x and y, and you're trying to do this again, then you're going to do the same thing. Does this look familiar? That's that magnitude of cross product. Okay, that's the thing from the previous section. The only difference is in the beginning, you have to evaluate that scalar function at x, y, and then z gets replaced with the function of x and y. So this is a nice little shortcut. Okay. I'll do an example, but before I do an example, wait, am I not going to do an example? Yeah, I'm going to do an example. Okay, so before I do that though, I want to show you something. I go beyond that, okay? In these notes, the recap notes, I go beyond this. So everyone, deep breath, pay attention. If you're trying to find the surface integral, Okay. Over some surface where your surface is drawn with some vector function, like the sphere, then you have to do this. This is what we just did in the previous example. Okay, that's what you have to do. Okay, now if for some reason your surface on top is your classic surface function of two variables. Now, I had to use G here, not F, because F is being reserved for the scalar function here. So not to be confused, this is the given scalar function we're trying to integrate. The surface itself is the nice surface from previous classes. If this is the case, then here's the formula. Okay? In the domain, D is the shadow on the ground. Okay, that I kind of explained in the previous section. Here's the new thing. What if your surface, okay, this time your surface is sideways? In other words, your surface is that y is a function of x and z. So it's surface out here this way, where the shadow of it cast onto the xz plane is your domain. Then that D is the restrictions here in the XZ plane. And then this is your surface. And here's how it simplifies. So let's see what the difference is between this one and the previous one, just so we don't lose sight of things here. In this one, you're going to take your scalar function. You're going to just replace X with X, Y with Y, and whatever the Z is, you replace it with this function. And then over here, it's partial with respect to x squared, partial with respect to y squared, and then plus 1. Then you take the square root. That's what happens in our traditional sheet in the wind. Now, if that sheet is sideways, you're going to take your scalar function. You're going to let x be x, z be z, and replace the y with it, whatever that function is. And then your two partials are with respect to x and z, not x and y. It's x and z this time. And then we have a third case. What if your sheet is the other way, where it's kind of, you know, this way, and the domain is, or the shadow is cast onto the yz plane. In other words, your surface is x is some function of y and z. Then there's another way, there's a shortcut for that one. You just take the scalar function, you let y be y, z be z, and this gets replaced with this. And then your partials have the y and the z instead of the x and the y, or the x and the z. Okay, so there's 3 shortcuts for 3 different scenarios. And then the one in the beginning is for surfaces that there are no shortcuts. So the first formula A here is for things like the sphere. You can't draw the sphere as a sheet because the shadow would go back upon itself and it wraps around, right? It would fail like this weird sort of vertical line test. So this is like the generic case, and then B, formula B, C, and D are like 3 special cases. With that in mind, are y'all getting sick yet? I would like for us to find this. All right, here we go. So find x ds, find the surface integral over the surface S of the scalar function x ds with respect to surface area, where S is the surface shown below, the entire surface. Now, if you're having trouble seeing that surface, there's actually how many surfaces here?
3.
3 of them. There's the back, there's the blue one there, there's the green one. So if we're gonna do the surface integral over the whole thing, we've got to do it 1 surface at a time and add up the answers. You ready for some fun here? You thought it couldn't get more fun. So S is actually the union of three other surfaces. So let's label these. I'm trying to think of which one I want to do first. I'll do this in a different order. I'm going to do this as S1, this one is S2, and this one is S3. So let's start with S1. So what we're trying to do right now is find the surface integral over S1 of x ds, right? So when you look at that surface, when you look at it, isn't that surface kind of a special case? I mean, this is just a disk in the, what plane is that in? What plane is that disk in?
YZ.
It's in the YZ plane, right? And X is always 0 on that plane. Wait a minute, did I just say X is always 0? I did say that, didn't I? Those words just came out of my mouth.
Yeah.
If we're on surface 1, right? If we're on surface 1, X is 0 all the time, right? But that just means that this is just double integral over S1 of 0 ds, right? Because my scalar function is whatever X is. And if X is always 0 when you're on that surface, then that's just 0. We got lucky, okay? We got lucky. All right, maybe S2 will be harder. Yes, it will be. Okay, so let's look at S2. Okay, so now I
So
want
there's
pardon me?
so there's no like area to the bottom.
No area.
We're calculating surface area.
We're not calculating surface area.
Okay.
Yeah, we're not calculating a surface area. We're calculating a surface integral. Think of it this way. Let's imagine that this X in here is our density at that point. Okay. So we're adding up all the densities. Well, when we're on the back side of this thing, when X is 0, according to the density function, we have 0 density everywhere, which means when you add them all up, you still get 0. Or you can think of it as temperature, right? If the X represents the temperature at that point, then if we are on that plane X equals 0, then we have 0 temperature. We got lucky. That's an easy one. Look, what about S2? Okay, so S2, we spent time last class being able to come up with the vector form for this, didn't we? And we all practice how to do it. However, I give you the equation here. X is 1 minus z. Another way of looking at that is that X is some function of 2 other variables, in this case, y and z. Although the y does not appear in the function, right? The y doesn't appear here. The z does, right? And that's just because of the shape of this. So what formula can I use here then? A, B, C, or D?
D.
D. I can use formula D. Do I need to show it or do y'all have it? I'll show it for this one. Formula D said that if you have that X is some function of Y and Z, then you can use this right here. By the way, all this stuff down here is just proving why it is what it is, like why it turns out to be this. You don't need to worry about that. Okay, so that means I can use this. Okay, so that means I can do, this will become this double integral right here. So the things I'm gonna need the partial of g with respect to y and z. Let me get those. Partial of g with respect to y is what?
0.
0, right? Because the function is 1 minus z, right? That's the function. So the partial of that with respect to y is 0. And the partial of that with respect to z is -1. And the scalar function we have, this is my f of x, y, z. All right, let's try this. I'm going to do the double integral over d. Okay, I need my scalar function evaluating. I need to replace x with what?
1 minus z.
Whatever the function was, right? With this, 1 minus z. And then I replace the y with y and z with z, but there are no y's and z's in here. I'm sorry, you replace the y with y, z with z. Yeah, so all we're really worried about, because this is just x, right? It's always just going to be whatever x was here, right? This is x is that. And then we need the square root of partial of g with respect to y was 0 plus -1 squared plus 1 dA. So this should give me double integral over d. Let's see, what is that underneath that root? Is that just root 2? Yeah, root 2. I'm just going to pull that out. Any questions on that part? We're not done, but any questions on that part? So look at this formula here. It says, okay, you're going to take this surface integral. It's going to convert to a double integral over d. D is the domain in the the YZ plane. So what is the domain of this blue surface in the YZ plane? The shadow of it cast up against that plane. What do you see?
It's a circle.
Circle of radius
1.
1, right? So if we look at that blue from this point of view, right, there's our circle. We know it's a radius of 1 because of this cylinder thing, right? So that means I'm going to need to go now and go to polar, because my domain in the YZ plane looks like this. And so watch how I do this. My y gets replaced with r cosine theta. My z gets replaced with r sine theta. And then theta is going to go between 0 and 2 pi. And r is going to go between 0 and 1. That means this double integral now becomes root 2. Now I can put my limits of integration. 0 to 2 pi, 0 to 1. 1 minus what?
R sine theta.
Z, right? But z is r sine theta. So r sine theta. And then dr d theta. And I left a space there for you again. Polar, right? You went to polar. Got to have an r in there. And that's it. This is the integral. That should all be doable now at this point. Let me see if I did that one. I think I forgot to put the square root of 2 on it. Where is it? Yeah, I think it's this one right here. Yeah, it's this one right here. So if you calculate that, I'm going to go ahead and write the answer down here just so we have it. If you did this, your answer should be pi. Okay. And remember, the one from up here, S1 was 0. And then we have pi, right? And now we need S3. You having fun yet?
Got a headache.
S3. I'll let you think about S3. So what I want you to be thinking about on S3 is, are we going to use A, B, C, or D? We haven't done anything E, F, G, H. Don't worry about those yet. Just see if you can't figure out which of those we're going to use. Don't say anything yet. I want everyone to think about it. I'll be right back. What's the verdict?
Say hey.
A? Are you doing that because that's like the generic one that will always work, or are you doing it because we have to?
Well, I don't see any kind of surface you can get that would work for any of the others because it's not a surface.
Hey, your wind tunnel, just lets you know. So what Benjamin's saying here is that the green surface, you can't look at it as being a true like function of two variables. And you can tell because the green surface is this equation. So you can't solve this for Y or Z without doing a plus or minus. And you know, it's because it wraps around the other side. But that shouldn't prevent us from doing the problem because we can draw that surface using a vector function. That's what we spent like an entire class period learning how to do. And it's exactly because you can't do this problem if you can't draw it, right? So unfortunately, we are going to, or fortunately, however you want to look at it, we are going to have to figure out what the green one is here in terms of U and V. There's just no, so we can't use a shortcut. All right, well, that's what it is. Okay, let's see if we can do that though. Okay, R of UV. All right, so, okay, so the way I'm thinking about it is if you're on the green surface, then you have to be on the edge of a circle of radius 1. And that should be in the YZ component should be dictated by the circle. So that means my Y, I'm going to call that cosine. I'm going to use U. And my Z will be sine U. And if I'm going to do that, then my U's got to be between 0 and 2 pi. Does anyone want to give me what the X component has to be? Think about this. Right now, what I'm drawing are going to be, I'm going to be drawing all these little circles. But I want the Y values, I'm sorry, the X values, right, to always be stuck in here somewhere. How do I stick those X coordinates between this and the backside?
Is it going to be 1 minus the Z component?
1 minus the Z component. Okay, yes and no, because I'm not quite sure what you want me to use for the
1 minus sine of U or sine of V?
1 minus sine.
I'm
Okay,
kind
let
of
me
going
put-
off a limb because we got this surface of X equals 1 minus Z.
Let me do
and I-
this. Let me do sine of U. That's 1 minus Z, right? what's wrong with this? So Daniel, you should look at that and realize that there's something's not right.
Yeah, we're definitely lacking a V.
Yeah, you haven't used V, right? So let me tell you what you've just drawn, Daniel. What you've drawn, Daniel, is you've drawn this edge. That's all you've drawn. Because this draws a circle, right? It tries to start to draw the circle, but you're forcing your X to be on that plane, not between. So this is too restrictive. This is too restrictive. You need this to have a little more freedom. So why don't we call this V, and then use the bounds on V to allow us to slide back and forth. And that's where you go 0. That would be the back plane up to the front plane, 1 minus Z, but you, Daniel said, is sine U. Does that make a little more sense now? Imagine we didn't spend over an hour doing this before, right? And I was just expecting for you to understand that, right? Like, even though we spent so much time doing it, it's still confusing, right? But if you can't come up with this, the rest of the problem is impossible, right? Okay, we are using the first one here, so let me go back and grab it so we can take a look at it. Notice on this note, I have a little thing here on the bottom. It says domain not visible. That's because in the special cases, B, C, and D, you can always see the domain cast upon one of the planes, like down to the ground or on the sides. But when you're doing like a surface where it truly is a function of U and V are like clocks in the background. And you're drawing the surface as these two clocks are running. So you can't visualize the domain here as a shadow of anything. I just want to point that out. All right, so we need to do this. Crap, look what we need to do. We need to take the scalar function and evaluate it on the vector, or on the vector function. And then we need to do the cross product of the partials. And we actually have to do it because we haven't done it for this one. So partial time. Partial of R with respect to U is 0, negative sine U, cosine U. Partial R with respect to V is 1, 0, 0. Are we that happy? We are that happy. RU cross RV. Okay, so, oh my goodness. What happens here? Cover this up, 0, we get 0. Cover the middle up. Okay, 0 minus cosine plus low cosine. Cover that up, 0 minus plus, I think we get sine U here. Questions? Did I do mine a little different? I may have, I don't care. We're gonna get the same answer. All right. So our magnitude now. All right, so what I'm doing here is I'm trying to figure out what this piece is. Okay, so magnitude, oh, are we, oh man. One,
isn't it?
What's that?
Or,
Yeah, sorry. 1, 0 squared plus cosine squared U plus sine squared U. That's going to be √1, which is 1. Oh, how lucky. How lucky for us. Okay, that's great. Awesome. All right, now what we need to do is this right here. The original function. What was the original function?
X.
X. Okay, so we're going to be doing the double integral over d of x, right, times 1 dA. That's where we are. But what is x? Hold on, we got to be real careful here. What is x? X, we have to replace it We have to replace that with what X is for us here, right? What is X for us? V. That's all it is V. So this is just V dA. And then now we can put the limits of integration. All right, now the order does matter here. 0 to 2 pi is the outer one. 0 to 1 minus sine of u. And then V d V dA. I mean, sorry, dV du. That's our integral. That should be pretty straightforward stuff. I mean, there's a little weird stuff. You get a sine squared in there, you'll have to do a power reducing, but it's all within Cal 2 difficulty integration. Let me see if I had my computer do that for me. I think I did. Yeah, it's this one right here. 0 to 2 pi, 0 to 1 minus sine of u of v dv du. I get 3 pi over 2. Okay. So without doing that work, we get 3 pi over 2. All right, we're ready to answer the question now. We had 3 pi over 2, and then the previous one we had 0 and we had pi. So the answer to this is 0 plus pi plus 3 pi over 2, which is 5 pi over 2. That sucks, huh? Having to do all those surfaces. All right. Shift gears now. Still in the same section. All right. Surface integrals are behind us. Let me see if I can't get your brain warmed up to this. I realize we're at the end of the semester and your brain's mush already, but if you go back and you look at our notes, we did line integrals where we had scalar functions. Okay, so what we were doing here is we were moving along a curve. And at every point we could say, oh, that's the temperature there, or the density or whatever. So we had scalar, okay, scalar here, but this was a line integral. Now what we've done is we've done surface integrals where we have a surface and we have some scalar function here. And this is ds. So this little s was like an infinitesimal little arc length. ds, little arc length. Here, ds is this infinitesimal patch. So it's like we've done like the same thing we were doing here, we've done here, but now it's a surface instead of a curve in three-dimensional space. If you go back and look at when we did this, the next step after this, we did line integral of f dot dr. So what we said is, okay, now imagine that this is a particle moving through a vector field. And so you're moving, we're trying to calculate the work done. Okay, so that's what we did. Right after this, we did this. So now what we're going to do is we're going to do the same thing here. We're going to say, imagine that your surface, and at every point you have vector field. Okay, and so we don't have this idea of work because we're not getting from one point to the other point. You're not trying to calculate the work. You're not trying to add up how do I say this? I don't want to get back into the whole thing. We had the vector field, we had a tangent vector, we tried to add them all up, and that gave us the total work done. Somehow we need to like add vectors here from the vector field. And this is what's going to be known as flux. All right, now let's get into, I just trying to get you to see that this does somewhat naturally, we are following progression here. We started scalar over lines or curves like this, line integrals, scalar, then vector field. Here we've done scalar surfaces, now surfaces with the vector field thrown in now. Okay, before we can do that, we have to give a couple of definitions. An oriented surface. So an oriented surface is a two-sided surface. And I say two-sided surface because there are examples of surfaces that don't have two sides. So has anyone ever heard of a surface that doesn't have two sides? Anyone ever seen a surface with only one side?
Like a
I
Mobius
have.
strip.
That one.
Yeah, the Mobius Strip. So if we look at this as just being a surface, I know that you could argue that this edge creates this is just like a box, like a shoe box that's really flat. Let's just not take into account the thickness of the paper. This is then a two-sided surface, right? So if I hold it, my fingers are on the two different sides. So now if I take that strip, there we go. I take that strip and I just twist it one time, twist it, and then paste it together. Sorry, it's so loud. My stapler is really loud. And I get this shape, and that's called a Mobius strip. And this is a single-sided surface. So if you put your index finger and thumb, then you would think you're on a different side, but if you follow the path around, you will actually wind up on the same side that your thumb is on. You go back around, you will still be on the same side. So your both fingers are on the same side of this surface. So this is an example of a single-sided surface. And there's other weird things in math. This all has to do with something called topology, not topography, but topology. That's an example of a single-sided surface. There's examples of containers that have zero volume. So like a container that has zero volume. I'll show you real quick. I'll go grab mine. This was a gift from one of my former students. It's a glass pipe. I mean, Klein bottle. Okay, so if anyone has ever seen a Klein bottle, this is a bottle this is an example of a container that has zero volume. And it's the same sort of principle that my finger is on the outside of this bottle, but at the same time on the inside. It's really hard to see it, but the surface curves and goes in. And then if you were to be on the inside, right, you're also on the outside. The problem with the Klein bottle is that in order to really see a Klein bottle, you need 4 dimensions. So the Klein bottle, the neck of it has to punch through itself. And that's the only way we can visualize it in 3-dimensional space. But this is our best example of it. And somewhere, I have another one. Hold on, let me see if I can find my other one. I'm wasting time, I apologize. I can't find it. I'm gonna get mad if my wife threw it away. So when I was in grad school, my buddy owned a bar, and I used to work at his bar, just help clean up and stuff, and he let me drink and stuff. And he bought me a mug that was a Klein bottle mug. Let's see if we can find it. Yeah, this is it right here. So it's hard to see it here, but This is basically a Klein bottle. So the inside of the mug is also the outside of the mug. So it's the same sort of shape, and there's a hole in here. It's hard to see it from this, but basically it's an example of a container with 0 volume. All right, so I used to have my buddy fill it up, and he never charged me for beer because basically there was no volume to it, right? So it was I wasn't drinking anything technically. So it was just a little joke, but okay, whoa, we're going way off. All right, I love topology. If you're a math major, you get topology. It's one of these really fascinating topics because I guess you can't stop me. Okay, so think about this. If I were to ask you to tell me the difference between a coffee cup and a donut, what would you say?
There is none.
What do you mean?
Well, they both have one hole. They both contain surface area. They both, I can't really think of a difference besides, maybe they contain a different amount of mass or volume, but there's nothing really that different from them.
Okay, so you're thinking of it very abstractly. Most people would think, okay, well, you can eat a donut. You can't eat a coffee cup, right?
Don't dare me to
So-
try.
Yeah. So like when you start
Pragmatically,
talking
it's-
about, what's that?
I mean, pragmatically, a coffee cup and a donut are two different objects that do different things, but
Yeah.
mathematically, it doesn't really make a difference. They are similar.
Okay, so that's the thing. How do we mathematically distinguish things? And you can't start talking about physical qualities. Okay, so you can't talk about mass, density. Any physical characteristics are not mathematical characteristics. It's purely, you have to do it from a very pure math perspective. So I'll give you just the real quick breakdown, the way it works. Topology. This is called point set topology. If I take a donut, okay, that's my donut, and I take a coffee cup that has a handle on it like this. I have to have a handle. Okay. Then what these two objects are mathematically equivalent. And the way it works is this. If you take any path, so start at a point, take any path on this donut that you want to take. You can even go along the other side or whatever and come back. As long as you come back to this point, imagine that path, and now imagine shrinking that path down to back to a point. So it's almost like a rope, and you're going to pull it in, everything's going to come together. If on this donut, every path can be shrunk back down to one point, unless your path goes here, goes around the inside of the donut and comes back to here. Then you can't shrink it down without passing through the donut, right? You actually have to like cut through the donut. But every other path that doesn't go around that would be able to be shrunk down. The same can be said for that coffee cup, that every path on here could be shrunk down unless your path wraps around the handle. And then you can't shrink it down without cutting through the handle. So mathematically, from a topological perspective, a coffee cup and a donut are mathematically equivalent. So that's where you learn about these things like Mobius Strip, Klein bottles, things like that, is in topology, which is just a fascinating subject. It's fascinating in the sense that what I thought was fascinating about it is there's really hard problems in math that were unsolved for a long time. And then topology came around, and they weren't even trying to solve those problems. And they realized, like, from what they learned with just the structure of topology and the way things work, like, oh yeah, that problem, that's easy now. And so it's like one of those things where we didn't realize the benefits that we would get from it. Like, it reaped more than we ever figured it would. And it's really just a cool subject, in my opinion. I loved it. Some of my classmates hated it, but okay. All right, topology. What am I talking about? Let me get back to this. Okay, so oriented surface. If we have a two-sided surface in which the normal vector at every point on its surface exists, and such that the normal vector varies continuously over the surface, that's what an oriented surface is. So if we have just like a sheet flowing in the wind here, right? That's a two-sided surface. I mean, as long as at every point there's some normal vector that's orthogonal to the sheet. Okay, that's what we call an oriented surface. Anywhere you move along that sheet, there's some normal vector, and it just kind of, as you move, the normal vector changes depending on the shape of the sheet. That's an oriented surface. When you have an oriented surface, there are two possible orientations, as we like to call them. We have positive orientation and negative orientation. So, oops, clear that. For a sphere, which is a closed surface, positive orientation is where we're looking at all the normal vectors as pointing away. And negative orientation is when we look at it as all the normal vectors pointing into the inside of it. Okay, so for every closed surface, there's either positive out or negative in. All right, also something to remember about normal vectors is that the way we get the normal vector, right, is to take the two partials and cross them, right? If we take two partials of our surface, if we can draw our surface with this, then if we take the two partials and cross them, that gives us a normal vector. And if we divide that normal vector by its own length, then we've created a unit normal vector, right? It's a normal vector with length 1. And then if we just take the negative of that, then it's going to point in the opposite direction, right? Okay, I'll get to this in a minute. All right, let's try and define flux. So the common analogy that we use for flux is a river, like a river that's flowing, right? You have water that's flowing down a river. And imagine casting a fishing net across the river. Now this net in no way stops the flow of the water, right? But maybe there's a way that I can measure how much flow is going through the net. That's what flux is. So if you have a space, so imagine we have in three-dimensional space here, a vector field. So remember, there's vectors everywhere here. You can't see them, they're everywhere, right? They're all over the place. This vector field fills the entire space with vectors. So at every point, if you're standing there, there's some, electromagnetic field or magnetic field, or if it's a flow of water, whatever it is. So this field is everywhere, okay? And we have a sphere sitting in that field. There it is. What I have here as an animation is us looking at a specific point on the sphere right now. So we are looking, we're standing at that point on the sphere. The green vector is the field itself. Okay, so if this were water, if this were a molecule of water, it would be wanting, at that point, it'd be wanting to move in that direction. And the length of that vector would be how strong that flow is in that direction. Okay, if it's longer, it's going to be going, with more force in that direction. Shorter, it's not so much flow. All right. Now, the black vector is the normal vector. That's the cross product of the two partials, and that's pointing straight up. Okay, so that's perpendicular to our surface. The red vector is the projection of the green vector onto the black vector. So what the red vector represents is the magnitude of the flow of this point in that direction away from the surface. Yes, the point wants to go in this direction, but that direction means over and up a little bit. And the up is the out, is the away from the surface. Does that make sense? At every single point, we have that, don't we? At every point on the surface, we have that. And so let me move around here again. I'm gonna move this point. I'm gonna move this point over to this one particular little, get over here. What are you doing? Come over here. There we go. I'm gonna move it to that patch there. So we have a couple of points on this little, now imagine that that patch is like an infinitesimally small little patch. And let's say I wanted to measure the flow out of that patch. Well, I'd have to look at different points, right, on that patch and look at the green vector, which would be the field, the black vector, which would be the normal vector, and then the red vector, which would be a projection. And I would have to do that for all these points in here. Here's at a few points. I could do that. What I'm showing you right now are just, come on. Those are just the normal vectors. Those are just the normals. Here's the field vectors for each of those normals. And then here's the projection of those onto the normals. And so let me take everything else out except for that projection vector. And let me get this guy out of here. And so basically that red is representing the flux, the flow out away from that surface, perpendicular, orthogonal to the surface. So it's like if you had the net and you had the water coming through the net, right? The net is that red patch, and the red vectors is the flow out of that patch away from the surface. That's flux. And we want to do it for an infinite number of points in there, right? And that will be able to in that sense, we'll be able to calculate the total flow through the patch. Does that kind of make sense what flux is? Vector field, normal, project onto the normal, figure out what that is, add them up on an infinitesimal patch, add that up on the whole surface, you have the flux of the whole surface. So what is the formula for it? What was the notation we use? Here's the notation. First time we're seeing that. It's the double integral over S, so some surface S, of the field. So someone's going to have to give us the vector field, and we're going to dot that. This is the new notation. Capital S with the vector on top of it. Do not confuse that with what we were doing previous problems, right? Previous problems. Right? Scalar function, D capital S was not a vector. Now, the notation is vector field dotted with, and then D capital S vector. Now, another way of looking at this formula is capital F, vector field dotted with the normal vector ds. So this is a way to use the surface integral that we just learned, same section. If you can take your field and dot it with the normal vector of the surface, then you can do a surface integral like the previous problems we've been doing. Or you can convert that over to this. Now, I think we're just going to have to stop here because I don't really have enough time. I just want to give you just first look at this. What we'll do next time is we'll do flux across a sphere. I'll give you the special cases. We'll do 1, 2, 3 more examples. And then at least I think we'll get to 13.8, which we might, we'll at least get a little bit into it. And that's, we had Green's theorem, and then we have Stokes's theorem, and then the last section, which we're not going to get to, is divergence theorem. So yeah, if I were you, I would do your homework or the review, start working on the review. Is there anything we can do on the review now? Anything more? Let's see. I'll show you what else you can do here. Does this all seem overwhelming at this point, or how are y'all feeling about this? It's a lot, huh?
I think I'm just a little too tired from the semester to be learning about flux.
Yeah. So I said last time you could do 17, right? Shit, see, 18 is flux. I guess 19 is flux too. Yeah. Yeah. 20 is Stokes's theorem. So is 21. Flux.
It seems like this would be used a lot in like electronics.
Yes. Engineering, electrical engineering, mechanical engineering, flux is used a lot. Okay, so unfortunately, we can't do anything else at this point, but I'm sure you're still working on the other parts of it too. So, okay. I guess Wednesday is going to be a big day then, huh? We have a lot to do on Wednesday. We'll see how it goes.
And the mini exam that you want us to do, the 7 with the review, when is that going to be due?
I did make that the day of the final.
Okay.
I started class today. I said, you know, if you do the review for the test, I'll count that as mini exam 7. You'll turn in the day of the review. I'm just sending you a Dropbox link for you to drop it in there. And then this mini exam 8, that is a question mark still, but I think I'm going to have you watch. This is an option. I mean, by this time, hopefully you have 4 mini exams done, but I need to think about mini exam 8. I'm not sure about that yet.
Is there any other lecture videos that you have for the stuff that we didn't learn? You know, if we just want to go over it for our own.
Yeah, I mean, I do think that I'm going to be rushing through this on Wednesday to get what I can. So if you go to my YouTube channel, there's a thing called Cal 3, a whole playlist on it. And if you go to internet lectures,
Writing's not that easy.
Are those
know.
just
I don't know.
hours? Oh no, those aren't hour classes, right?
yeah, these are lectures from like a traditional face-to-face class. It's so we're stopping like these last two here, Stokes' theorem and divergence. This is usually takes me 3 days to do what I'm trying to do here in 2 days. So I don't know. So yeah, you could watch this. It's just basically me going through these notes.
Why is our
Okay, yeah, thank you.
Yeah. So that's all there. And then also,
Writing's not that easy.
I don't know why I'm
but
getting
usually
ads.
can help.
Maybe, I don't know. And then there's solutions. You've known about this, hopefully. And for those sections on Stokes' theorem, it's me working through problems, right? So it's all out there. Okay. Any other questions? You're free to go. Any other questions? I know, Daniel, you had a question.